Good morning. Let's continue on the phasor domain, AC circuit analysis. So last lecture, we discussed how to make phasor domain and phasor domain inverse for both voltages and currents. Then we discussed about the impedance, which is something similar to the complex resistor, but we will not consider it as a resistor because most likely the resistor definition is related only to a real parts. So we will call it as an impedance, which will be a complex number that has a real part and imaginary parts. The real part is called resistance, which is the resistor that we know, while we have another thing, a new component, which is called reactance. This is the imaginary component of the resistor or of the impedance. Then we have a complex number for impedance, complex number of voltage, complex number of currents. Therefore, V will be I times Z, and all of them are bars because all of them are complex numbers. Then Ohm's law, in DC, we used to say V equal I times R. In AC, now V bar equals to I bar times Z bar. Then our target next is how to convert to phasor domain for the circuit elements. So we know like that we have sources, voltage source, current source, and we know how to convert the voltage and the currents to phasor domain, VRMS angle. And while we have here the other circuit elements that we have resistors, inductors, capacitors. Now let's make or see how we can make the conversion between time domain and frequency domain. So here is time domain. Here is phasor domain. And recall from the complex numbers, J, which is the same as I, the same as square root of -1. Since we are in electrical engineering course, then we will use simple J, not simple I. But whenever you do it in the calculator, you need to insert it as I, not as J. Then, let's see how we can convert every element to phasor and time domain. So the resistor, this is the symbol of the resistor. In time domain, it is a resistor R, and the units of it is omega. Now our target is to convert this to phasor domain. Phasor domain means the resistance will be converted to be impedance as Z. So it will be Z bar of R, which is for the resistor. So the impedance unit is in ohms. Then we need to convert the resistance to impedance. Since it's still in ohms, so there will be no change actually. So the resistance, the impedance of the resistor will remain as R. No change. And it is in ohms. How about the inductor? The inductor, this is the symbol of the inductor. So L, which is in Henry. Now we need to convert this to be impedance. So we call it ZL bar. So we will call it bar because, again, like the impedance is complex number. So what's the value will be? It will be J times omega. Omega is the angular frequency, which is 2 pi times F, times L. J omega L. And the unit will be ohms. No longer will be Henry, it will be ohms. And keep in mind, J omega L, sometimes we can write it as JXL, such that XL equals to omega L without the J. Okay? Then, for the capacitor we know it is simple C, and the unit is in farad. That was in time domain. In phasor domain, it will be impedance. So Z bar of the capacitor will be 1 over J omega C. Okay? And the units is in ohms. 1 over J omega C. And also you need to know that from the complex numbers property, 1 over J equals to -J. That's one of the complex numbers property. So we can say 1 over J omega C is actually -J times 1 over omega C, or over omega C. Okay? Sometimes we can donate xc by 1 over omega c. So z c bar, it can be rewritten as negative jxc. So if you want to use the symbol as xc, or you want to use symbol 1 over j omega c, that's fine. But what I like is to use 1 over j omega c, j omega l, or j omega l. That's what I like. And of course, all of this is the unit in ohms. So that's it. So as a result, whenever we are dealing with AC circuit analysis, when we convert everything to phasor domain, every capacitor will be replaced by 1 over j omega c. Every inductor will be replaced by j omega l. So the good point about this, everything will be in ohms. The capacitor in phasor domain will be in ohms. Inductor in phasor domain will be in ohms. Resistors are in ohms. Then all of them are in ohms. So what's the best thing, or how can we use this, or what's the benefit of this? You can make series and parallel of the inductors and the capacitors without problem, because all of them are in ohms. Or in other words, all of them are impedance. You will no longer say this capacitor is capacitor. You'll say it like it's impedance. Then you can make series and parallel. Then you can say this inductor and this capacitor with the resistor are in parallel or are in series. Then you can group them together. Then the circuits will be, instead of to have voltage source, current source, resistor, inductor, capacitor, the circuit will be voltage source, current source, impedance. Then you can combine the impedance, like whatever I used to combine the resistors in DC circuits. So which will make it much easier. Then when I solve the circuit, I can find Z equivalents, I can do KVL, KCL, Ohm's law, the same techniques that we learned before, we can do it here. Then the problem will be much easier. Then I don't need to use the differential equation techniques. So the overall procedure will be convert the circuit from time domain to phasor domain. So all of the circuit will be voltage source, current source, impedance. Then you can combine the impedance, whatever you need, like what we used to do in DC circuits, and do parallel series, do the KVL, KCL, Ohm's law, find the unknown current, unknown voltage. After that, do phasor domain inverse. Convert phasor domain, return back to time domain. Then that's it. So that's how overall the way why we use phasor domain, because everything will be in ohms, then the circuit will be much easier for us. Then there is also another definition called admittance. What's this definition? Most likely, this is just for your information. I mean, I'm not willing to include this in the course, but however, we know in Ohm's law, V bar equals to I bar times Z bar. If we need to calculate I bar, it will be as V bar over Z bar. But whenever we deal with matrices, it will be as I bar as a vector equals to Z bar inverse as a matrix, then V bar times V bar. So we can donate 1 over Z bar by saying we will call it as Y. So Y equals Z bar inverse, or in other words, 1 over Z bar. What's the point of doing this? We can say direct I equal to Y times V, Y bar times V bar. Okay, what's the benefits? So basically, if we do some iterative techniques or put this in software like MATLAB or any other softwares, we need to do while loop or for loop maybe 1,000 times or 100 times. So we don't need to calculate the inverse inside the for loop. Calculate the inverse 1,000 times. Calculating the inverse using the software will consume a lot of time and will take a lot of computational time, computational effort. And this is something that we don't need because the variables y or the variable z are constant, which is the network. So we will calculate the inverse once. Then after that, inside the for loop, we will put the simple y. So y is actually the inverse of the impedance. And it is basically, we will use it in programming, most likely. In programming, so it can be easier for us to do the analysis. And since y now is complex number, so y equals to G plus J beta. Real part and imaginary part. So G is called conductance. Beta is called susceptance. So these definitions, again, you don't need, just for your information, it will not be included in this. So I mean, it's just like for your information. And the unit of it is ohms inverse, or in other words, it's Siemens. So we will, this is again used only for programming, but we will not use it in our analysis. Okay, then the overall in AC circuit analysis, after we convert everything to phasor domain, keep in mind everything will be complex numbers. So KCL, KVL will be the same as we used to know before. The sum of the leaving currents will be 0. KVL is the sum of the voltages across the loop, it will be 0. So that's it. Sum of the currents equals 0, sum of the voltages is 0. So we know how to do KVL, KCL. The same procedure as we used to do in DC, but the difference here is all of them are complex numbers. Okay? So the complexity of this is not in the approach, so most likely you know, okay, I know I'm going to do KVL, I'm going to do KCL, or I know how to do with this properly, but the thing is the math, or the complex numbers, or sometimes the lack of experience in dealing with complex numbers. So please make sure, try to practice on the complex numbers, how to try to solve some problems. And what I encourage you for the complex number, you don't need to do it in the handwritten way. Practice using the calculator. So doing it in the handwritten way will take a long time. While if you do it in the calculator, learn how to use it in the calculator, and when you get this tool or get this practice very well, it will be very easy. Now, how we do the combinations? Series impedance, parallel impedance, and two parallel impedance. How we can find this? Basically, the first step, convert every phasor domain, every time domain to phasor domain. How can I make sure everything is phasor domain? Make sure all of the elements of the passive elements are in ohms. Whenever you see ohms in the capacitor, ohms in the inductor, then they are all in phasor domain. If they are in farad or Henry, then no, I need to convert them to phasor domain. And how we can apply series if there are two or more elements are sharing the same current. Parallel, the same two nodes for two elements, share a common in two nodes. While short circuits, if they are short circuit, we can say if they are the same nodes at both ends. That's how we used to do. And we know how to do it with this. Let's give a small example. Let's assume we have Z1 bar like this. We have 10 ohms, we have J8 ohms. Then, the other thing, we have Z2 bar, 15 ohms, negative J2 ohms. So, by looking at this, everything in phasor domain, so everything in ohms, the capacitor in ohms, inductor in ohms, then that's fine. I don't need to convert them to phasor domain. The next step, I need to calculate Z1. So look at Z1 bar, 10 ohms, or the inductor and the capacitor, are those sharing the same currents? Yes. Then I can make them as a series. Okay, how? If they are all in ohms, they are all impedance. So I'm no longer saying this inductor, this capacitor, this impedance and this impedance are in series. So their series will be their sum. It's going to be 10 plus J8. J8 and 10, you cannot add them together because it's complex number. And this is a representation of rectangular coordinates. So we can keep it like this. You don't need even to use the calculator. It's 10 plus J8. That's it. So we know how to, the rectangular coordinates, the polar coordinate. Most likely, when we use for the impedance, keep it in rectangular coordinate like this. You don't need to convert this to polar. Let's keep it like this way. Then the next thing about Z2. Z2 bar, we will make them in series. So 15 and negative J2 are in series because sharing the same currents. So it will be 15 minus J2 ohms. And of course, the units ohms for both. Now the concern, okay, I grouped them. Now what should I put the symbol for? Should I put a resistor or inductor or what? Now it's a complex number, so we cannot put in resistor. We cannot put inductor. So what should I put the symbol? Put a box. Whenever we have a complex number, you can put it as a box. This is a box for Z1. This is a box for Z2. Okay, so we can avoid the confusion. Is due since what should I put the symbols in the circuit, equivalent circuit, then just put a box. Now, I'm gonna do some simplification. Let's assume we have this elements A. Here is Z1 bar. Here is Z2 bar. Here is B. We need to calculate ZAB. What do you think ZAB will be?
Z1 bar plus Z2 bar.
Z1 bar plus Z2 bar, because Z1 bar and Z2 bar are in series. So we will say that ZAB equals to Z1 bar plus Z2 bar, which is going to be as 10 plus J8 plus 15 minus J2. So 10 plus 15, 25. J8 minus J2 plus J6. Okay? And don't forget the unit ohms. How about another thing, which is we have here Z1 bar, Z2 bar. Here is A, here is B. We need to calculate ZAB. So what do you think ZAB will be?
Z1 bar times Z2 bar over Z1 bar plus Z2 bar.
Correct. So basically, what's the relationship between Z1 bar and Z2 bar? Parallel. So ZAB will be their products over their sum. So it's going to be as 10 plus J8 times 15 minus J2 divided by 10 plus J8 plus 15 minus J2. So when we discussed the complex numbers, we used to say, let's convert this to polar, then do the multiplication, then convert them to back to series, and other things. So we used to do it like before and using the handwritten. Now, when you do it using the calculator, you don't need to do any conversion. Just insert this expression as is in the calculator. Keep in mind, I encourage you when you do it in the calculator, put a brackets for any complex numbers you need to add. Just put a bracket, so to avoid any just confusion that can happen. And J again, of course, will enter as I. Then you can do it in the calculator. So you just enter this expression in the calculator and convert the answer to rectangular coordinates. So the final answer will be 7.19 plus J2.28 ohms. This is the AB. And that's it. Again, when you do this using the calculator, you don't need to do any conversion or don't do it in the manual way or in the handwritten way. Make sure the calculator will do the whole job. So your job now is to practice in how to use the calculators in solving the complex numbers in the right way. Okay? Sometimes some calculators can be different than before, so there are some procedure, then you need to know, you need to learn how to use this. Okay, so also a quick note what you will see in the textbook and what you will see in the notes. So in the textbook, they did find the phasor domain for the voltages and the currents as V bar equal to V max angle alpha. While in our notes, we used V bar equal V RMS angle alpha, or in other words, V max divided by square root of 2 angle alpha. So the thing which is we have divided by square root of 2. This is a difference between the textbook in chapter 5 and between our notes. So why there is a difference? So basically, in phasor domain, there are two opinions. Some people, they say, let's use the max notation. Some people, they say, let's use the RMS notation. So the textbook in chapter 5, they use the RMS, while some other textbook, they use the max, while some other textbook, they use the RMS. Personally, I prefer to use the RMS, not the max representation. Okay, even in this textbook, in chapter 5, they use the max, right? But whenever you go to chapter 7, they will switch to the RMS. When they go to the power calculation, they will switch to the RMS. Then how can they know, or how can you know, is this the RMS or is this the max? When you find, for example, the voltage, whenever you say the voltage is, for example, 10 angle 0 volts, if you put volts alone, this means, and that's in the textbook, the max notation. But if you wrote like V equal 10 angle 0, V sub RMS, then this is the RMS. So this will create some confusion. That's thing that I dislike or I don't want, which is why we need to have two representation. Therefore, I said let's use the RMS notation. Then we will not use the max. Then again, in the textbook for chapter 7, you will see that chapter 7 they will switch to the RMS notation. So since we are going to switch to it later, why need to use it? Let's keep the RMS. Okay? So when you go to the textbook examples, or even when you go to some of the answers of the recommended problems, then you will see there is a difference only in the phasor domain. But even though, if we use the RMS or if we use the max, the final answer must be the same for everything. Okay, it's just like the way that's what they used to do. So that, again, the RMS notation, this is in our notes, and this is also in chapter 7 in the textbook. Now let's go to worksheets number 8. Worksheet number 8. Recall worksheet number 1, which is the equivalent resistance. Worksheet number 8, the same as number 1, but it's called equivalent impedance. So basically, series and parallel. So we know how to do the series and parallel. So the first thing is to convert all of the elements into we call it ohms, or to phasor domain. So the resistor will same as is, inductor j omega L, capacitor 1 over j omega C. Okay? Such that omega equal 2 pi times f, it must be given. If it is not given, assume the frequency 60 Hertz. So it must be given in, sometimes it can be given direct way, this is the frequency, or it can be given indirect way. Okay? So you need just to make sure to read the question carefully, then you can see. Again, if the frequency is not given, assume it's 60 Hertz, then f is 60 Hertz, omega will be 2 pi times 60, which will be 377. The first step, we know how to, which is identify all of the nodes after converting everything to ohms. Then two series elements if they are sharing one node, and I would say like also sharing the same currents. Sharing the same currents. Then those are in series. Parallel, if they are common, sharing two nodes. Shorted the same nodes in either side. Okay? That's it. We know this. But the difference is we will deal with complex numbers. And the same thing, we will do capacitor and resistor in series. That's fine. Or we can merge them because they are no longer capacitor, no longer inductor. They are again called as impedance. Then we can combine them. So we will combine them like what we combine the DC resistors. Here is an example. We need to find the equivalence. By looking at this circuit, the first step, convert everything to be in ohms. Is everything in ohms here? Not really, no. We have this inductor, this capacitor, this capacitor. Two inductors, two capacitors. Then how can we do this? So the first step, capacitor will be 1 over j omega C. This is 1 over j omega C. This is j omega L. This is j omega L. Okay? We know L, we know C, all of them are given, but the thing is how to find omega. Read the question carefully. Then it will tell you the frequency is 10 Hertz. Don't substitute omega as 10 Hertz, no. You need to say omega equal 2 pi times f. which is 2 pi times 10, then it's going to be 20 pi. That's what we'll substitute omega. Okay? Then, now I'm ready to do the analysis. So I will say, for this capacitor, it's 1 over J 20 pi times C, which is 1.99 milli, means 10 power negative 3. Don't forget the milli, don't forget the micro, or the kilo, or the other thing. In case if you don't know exactly what's this, please ask during the quizzes or the exams, ask and we will give you the answer. Please make sure the milli, kilo, micro, nano, pico, mega, giga, all of this you need to know what's everything, what does this mean. Then, for this inductor, J omega L will be J times 20 pi times L, which is 79.58 times 10 power negative 3 because it's milli. Then for this capacitor, 1 over J omega C, 1 over J 20 pi times C, which is 7.96 times 10 power negative 3. For the other inductor, J omega L will be J times 20 pi times L, which is 159. 159.2 times 10 power negative 3. Then how to do this? Using the calculator. Actually, sometimes you don't need, when you do this, you don't need to write the J in the calculator because we know J will be a common factor. For example, in J omega L, here is J. Then what you will write in the calculator, 20 pi times 79.58 times 10 power negative 3 as a real number. So this will be as 5. So this will be J 5 ohms. The other one, J times 20 pi, 159.8 times 10 power negative 3. This will be 10. So it's J 10 ohms. So J will be as a factor. While for this expression for the capacitor, 1 over J negative J, then what you will enter in the calculator, 20 pi times 7.96 times 10 power negative 3. That's what you'll substitute in the calculator. So it will be negative J. Then the answer will be 2, so negative J 2 ohms. Then for that one, the same thing, it will be negative J. Then put the other in the calculator, it will be 8, negative J 8 ohms. Okay? So you need to be clever on how to do this in the calculator. You don't need to put 1 over J. 1 over J is negative J. Just put the constants to find the answer. So you can save more time. The next step, after we find all of the ohms in every element, redraw the circuits and write the new values in ohms. This is highly recommended. So you can have a good image what you need to do next. So the next step, I'm going to redraw the circuit and draw the new values. That's what we have. Those are the new values. Okay? So again, it's very important, very recommended. After you convert everything in ohms, redraw the equivalent circuit. Now I'm going to redraw the equivalent circuit, everything in ohms. Let's do the procedure. Everything in ohms, and we can combine them together. There's no problem with that. So according to our steps, let's label the nodes. Labeling the nodes, you can label them as scalars, you can label them as node 1, 2, 3, 4, up to 6, so the 6 nodes. So whatever you feel more convenient, it's good. Then by labeling the nodes, you will realize that the 8 and negative J, this resistor and this inductors are in series. They are all in ohms, and we can combine them. Then 4 ohms, negative J 2 ohms are in series as well. Then we can combine them together. Okay, what's there? I need to replace them. When they are in series, we will replace them by a box. So their equivalent will be 8 minus J8, and here 4 minus J2. We cannot say 4 and 2 add them together, and we cannot say 8 minus J8 together because they are different coordinates. It's complex numbers. So it will be like this. Then their equivalent will be as a box. So this is Z1 bar, which is 8 minus J8, Z2 bar, which is 4 minus J2. Now I'm ready for doing extra simplification. So again, as we know in finding equivalent resistance, now it's finding equivalent impedance. After you do every step, we will redraw the circuits for doing more simplification. So we have Z1 and J5. Again, start from the furthest point away from your observation. So Z1 and J5 are in parallel.
Right.
Between yellow and green, yellow and green. then we can do their parallel. So there will be 8 minus j8 times j5 over 8 minus j8 plus j5. Enter this expression as is in the calculator. Then it will tell you the answer. So the answer, I think, will be 2.74 plus j6.03. Okay? So the next step, redraw the circuit with this simplification. So it's called Z3. This is Z3. Now, we can say Z3 and Z2 are sharing one node, common in node, green node, and then if there is a current, they're sharing the same current, right? Therefore, they are in series, then add them. Z2 and Z3 will be added together because they're in series, then this yields to this Z4. Then we will say that Z4 and J10 are in parallel. So their equivalent will be Z4 times J10 over Z4 plus J10. So put this in the calculator, so you will get Z5. So Z5 will be like this. Then Z5 and 10 ohms are in series, right? Then they are in series, add them together. So Z5 bar plus 10 ohms, then you will get the answer Z equivalent. That's it. Problem done. Okay? So in summary, solving the circuits, these are the equivalent resistance, equivalent impedance, the same as equivalent resistance. The difference is the first step, convert everything to ohms. The second step, or the second thing is, second difference is we are dealing with complex numbers. Otherwise, the same. Labeling the nodes, series, parallel, short circuit, etc. The same techniques that we've seen before. Any question? Okay, now we are done with this worksheet number 8. So I just want to go to worksheet number 8. Now, let's go to solving AC circuit analysis. How can we solve the AC circuit analysis without the need to use the differential equations? The first step, converting the circuit into phasor domain. So we will start from the sources. Replace every voltage, every current source to phasor equivalence, which is the RMS notation. VRMS angle alpha, IRMS angle beta. The second step, convert the passive elements, resistors, inductor, capacitors, to their equivalent impedance. So you need to find the equivalent impedance, to the impedance, everything to the impedance. So everything will be in ohms. Then we can use KVL, KCL, Ohm's law, the same thing as we used to do before. And Ohm's law can be applied for inductor, can be applied for capacitor, that's fine. How? If and only if they are all as impedance, which is in ohms. Okay? Okay, let's continue. So the third step, using Ohm's law, KCL, KVL, to find the unknown thing. Unknown voltages, unknown currents, etc. Then what else? Don't forget the last step, which is converts your answer back to time domain. Converts your answer to time domain. If required. So don't forget to convert it to time domain if required. Sometimes some practice problems you don't need to do. But I mean, most likely the overall target is to convert it back to time domain. Okay? So that's the overall procedure. And also I encourage you to go to worksheets number 9 and 10. I'm sorry, number 9. So it's also summarize the procedure and how we do the analysis, and there's an example associated with it. So this can be as self-study for you, and the examples is written in details, deep details, how we find the answer. So you can look at it by yourself. So I'm gonna write here, go to worksheet number 9. So worksheet number 9 basically summarizes the procedure that I wrote here. and there is an example written in details in how to find the answer. Let's go to this question. This example number 1. Determine the current supplied by the source and the voltage dropped on each element. We need to find I source and all of the voltages. If we have the voltage source given, we have the voltage source expression. So the first step before doing any analysis, keep in mind you need to convert this circuit to phasor domain. That's the first step before even analyzing the question and see what we need to find. Let's convert everything to phasor domain. Some of the problems will be converted to phasor domain. Some of them, no. How can I know if this is phasor domain or not? Look at the circuits. Is there a time? Yes, there's a function of time. There is a cosine, right? So it's in time domain. The other thing, look at the inductors and capacitors. They are not in ohms, they are in henries. Therefore, those are in time domain, not phasor domain. However, some practice problems, if you realize everything in ohms and the source is given as a complex number, then the first step, you can skip it because this circuit has already been written in phasor domain. But with this problem that we have now, it's not. So we need to convert everything to phasor domain. According to our procedure, let's start from the voltage and the current sources. Then we will do the passive elements. So we have this voltage source, V equal 141.4 cosine 370.17. So it's given as a max representation. We need to find the RMS, the phasor domain. V bar is actually V RMS angle alpha, or in other words, V max over root 2 angle alpha. So VR max is 141.4 over square root of 2. What's alpha? What do you think alpha? Let's write the expression. It's V max cosine omega t plus alpha. What's alpha? 0. Right. Angle 0 volts. 0 degrees. And don't forget to write the unit volts. So 141 over 4, it will be 100 over root 2. 100 angle 0 degrees volts. So we done the first step, we did convert the source. How about the next step, which is the passive elements? The resistor 8 ohms will be the same. 6 ohms, it's in ohms, will be the same. Now then we have inductor and capacitor. Let's start with the capacitor first. So the capacitor, ZC bar, which is 1 over j omega c. Or in other words, negative j times 1 over omega c. Now, we know c. What's omega? Shall we assume omega? Is the frequency given? Shall we assume, or do we need to assume omega as assuming frequency 60 Hz then 2 pi times 60? What do you think?
We use omega. See cosine there.
Exactly. The frequency here given in the cosine. That's one of the ways that the frequency can be given indirect way. It's given indirect way. So some of the tricks, they say, okay, there is no information about the frequency, then we will say assume it 60 Hz. No, it's given in the cosine, in the time domain expression. So this is one of the tricks that you need to be figured out. So here we realize that omega equal 377 and radian per second. Again, it's given in the time domain expression. So if there is a frequency is not given, look for the time domain expression to see is it given or not. So 1 over 377 times c, which is times 0.633 times 10 power negative 3. So what you need to do, you will put only this in the calculator. Don't put negative j. Put this in the calculator, so the answer will be 4. Then it will be negative j4, and the unit is ohms. The next thing for the inductor, ZL, which is j omega L. J times omega 377. L is 26.53 times 10 power negative 3. Then you will put this in the calculator. J will remain as J, so it will be J times 10 ohms. Okay? Now, we did convert the capacitor, the inductor. That's great. The next step is to redraw the circuit and find the new, or put all of them in ohms, the ohmic value. All of them are in ohms. So what we're gonna do, redraw the circuits and put the new values in phasor domain. This is 100, angle 0 degrees. This is, we calculate it as negative J4 ohms. This is as J10 ohms. Now everything in ohms, right? That's great. Then again, reread the question and see what do we need to find. One of the things that we need to calculate is the currents, the source currents. So the source current is located here. We will not say IS of t because it's phasor domain. We will say IS bar, uppercase, and we will put it as again, like we'll put it bar because it's complex number. We are in phasor domain. And also a quick note: whenever you solve for voltages and currents, the final answer must be written in polar formats. Whenever you solve for the impedance, final answer in rectangular formats. This is a must that we will use in our analysis. Okay? So our target is to find the source currents. How can I find the source currents? Treat this problem as DC, but with complex numbers. How can I find the currents?
Find the equivalent resistance.
Yes,
And then you
you can use Ohm's law. Right. But we will not say find the equivalent resistance. We'll say find the equivalent impedance. That's why we prefer to use impedance other than resistance. And it's correct. So our target is, we will find the equivalent impedance. So I'm going to redraw the circuits and find the equivalent impedance. The equivalent impedance will be as a box, call it Z equivalence. Then here is V source. And keep in mind, when we plot the source, we will plot it like this way. Why we plot it like this way? It's like sine or cosine signal to distinguish this is AC source. How about the polarity? The polarity will be like this, plus minus. So we will put the polarity outside of it. While the DC source used to be like this. That was in DC. AC, we will use like this. Okay? Just for your information. Yes?
Do we change what current source looks like too?
No, the current source will be like as is. But here just like for the voltage sources. And again, why the symbol look like inside it looks like sine or sinusoidal. That's, I mean, that's in purpose because some other things in maybe in other courses, not in optical engineering, so like it can be like this is triangular or square wave like this. So you'll see something different. So in purpose, we put it as cosine signal to make sure to let you know that this is sinusoidal waveform. Okay, then our target is to find Z equivalents. So we can say that I source equals to V source over Z equivalents. That's the key. That's how we find I source. So now the problem is how to find Z equivalents. Let's isolate this part, or let's look at this part. We don't need to isolate it actually. We can simplify it like this way. Label the nodes. This is yellow node, pink node, orange, and green. Now look at the negative J4 and J10. Are these sharing the same currents? Yes, these are sharing the same currents. So these two elements are in series. So we will say that negative J4 plus J10 are in series, so their answer will be J6. Then what I'm going to do, redraw the circuits. What the new simplification? Here is 8 ohms. Here is 6 ohms. And this is their equivalence that I'm going to call it as Z1 bar. This is Z1 bar, which is J6. Then that's it. So the next step again, redraw, relabel the nodes. So Look at Z1 and 6 ohms. Are those in series or parallel? Parallel. So we will say Z1 bar, or I would say like Z2 equal to Z1 bar parallel with 6 ohms. So which is going to be as Z1 bar, which is J6 times 6 over J6 plus 6. Then you will insert this in the calculator as is. So the answer will be J3 plus 3 ohms. Then the next thing, redraw the circuits again. Here is V source, which is 100 angle 0. Here is 8 ohms. This is Z2 bar. Okay? Which is J3 plus 3. Now, what's the relationship between Z2 bar and J8? Series. Then we will say that Z equivalent will be 8 plus J3 plus 3, which is J3 plus 11. Okay? That's the equivalence. Then in order to calculate the currents, we say that we are ready to calculate the currents. So I'm going to redraw the circuits. 100 angle 0 degrees. This is the equivalence. Then to calculate the current I source, it will be as V source over Z equivalence using Ohm's law. So V source 100 angle 0 over Z equivalent, which is J3 plus 11. Then you need to substitute this using the calculator. Keep in mind, any number angle 0, you don't need to put the angle 0 in the calculator because any number angle 0 is the same. So for example, 100 angle 0 degrees is the same as 100. So when you enter any number in the calculator angle 0, you don't need to enter the angle. So you can avoid more complexity. It will be 100 over J3 plus 11 here. So the answer, keep in mind, we need to make it in polar. So 8.77 angle negative 15.26 degrees amperes. I source. Again, whenever we are dealing with voltages and the currents, they will be in polar. While whenever we have impedance, will be in rectangular. Now I'm not done yet because remember our target is to calculate IS of t, not IS bar. So the last step, convert this back to time domain. How to convert this to time domain? Again, I'm going to rewrite it here. IS equal 8.77 angle negative 15.26 degrees amperes. This is actually equivalent to here. This is IRMS angle beta. So how to find the time domain expression? We will say IS of t is actually equal to I max cosine omega t plus beta, but we have the RMS. So there is the other format, which is the RMS representation, square root of 2 times IRMS cosine omega t plus beta. Now we can substitute it. So IS of t equal to square root of 2 IRMS 8.77 times 8.77 cosine omega t, omega is 377 given in the question, t plus beta. Beta here is negative, so it's negative 15.26 degrees, and it is amperes. You can stop here, or you can say square root of 2 times 8.77, which is, it will be a number, actually I don't know exactly, cosine 377t minus 15.26 degrees amperes. Then we will say that, okay, problem done, that's what we need to do in the calculation. Okay? Is this clear? So next lecture we will go to solve another example. That's overall plan. Then we will start the complex number. So we will end chapter 5. And next lecture I will give you the recommended problems that you need to see. But right now your homework is go to worksheet number 9, read it, and read the example associated with it. So see you in